don't understand this.
In physics, Loschmidt's paradox, also known as the reversibility paradox, highlights a conflict between two fundamental ideas: time-reversible dynamics. The fundamental laws governing particles, such as Newton's laws of quantum mechanics, behave the same whether time moves forward or backward. In other words, these laws do not prefer one direction of time over the other.
How do you know that?
Time travel has not yet been invented.
And the second law of thermodynamics.
I object, Your Honor.
What you mean by time can be reversed? What is time-reversible dynamics?
Time-reversible dynamics refer to systems where the fundamental equations governing their evolution remain invariant under time reversal, meaning the dynamics would look the same if time were to run backward. A mass attached to a spring oscillates back and forth with simple harmonic motion. If you reverse the time direction, the same oscillations appear, only running backward. The motion of two planets or celestial bodies interacting under gravitational force is time reversible. If you reverse their velocities, the system retraces its path.
I understood what he was doing.
But why?
Because Loschmidt's paradox is a collision between time reversal dynamics and second law of thermodynamics.
Don't give me that look.
Okay, what is the second law of thermodynamics?
The second law states that in an isolated system, entropy, a measure of disorder, always increases over time. Systems naturally tend to evolve from order to disorder, making certain processes irreversible. For example, melting ice caps cannot refreeze into their original form, and volcanic eruptions release heat and gases that do not spontaneously return to the magma chamber. The paradox arises from this question: if microscopic laws are reversible, why do we observe irreversible behavior in the real world? To understand this better, let's explore entropy. Entropy is a measure of disorder, randomness, or uncertainty in a system. Low entropy means low disorder, or more organization. High entropy means high disorder, or more chaos. The second law of thermodynamics tells us that in an isolated system, total entropy always increases over time. This is not just theoretical, it is an empirical observation based on real-world evidence. Now think of the universe as an isolated system. At its origin, the universe was like a cube, a highly organized, low-entropy state. Over time, it expanded and became more disordered, similar to a sphere, a state of high entropy. Moving forward in time, the change is easy to predict. Things become more disordered and entropy increases. But reversing time introduces a challenge. If we reverse time, the system becomes unpredictable. The universe would evolve through chaotic and inconsistent shapes, making it impossible to identify neat, symmetrical patterns like those we see when time moves forward. Without such patterns, it becomes impossible to predict what will happen next, even if we rely on empirical evidence. Fundamental physical laws are time reversible, meaning they allow time to flow both forward and backward. However, the second law of thermodynamics describes real-world processes as irreversible. Entropy always increases, and systems grow more disordered. This creates a puzzling contradiction. If microscopic laws are symmetric in time, why do macroscopic systems behave irreversibly? Even though the increase in entropy is a well-established observation, We cannot derive this irreversibility from the time-reversible nature of fundamental physical laws. This unresolved conflict is what we call Loschmidt's paradox.